Welcome to the test review video for sections 3.1 through 3.4. Everything that is written in black is going to be covered explicitly in practice problems in this review, and then the two topics that are written in white are not going to be covered but will still be on this test. Yes, technically the equation of a tangent line was first introduced in section 2.4. However, this idea permeates throughout chapter 3 and beyond, so it will be on this test. So if that's something you feel like you need to review, I would recommend going back to section 2.4. These are where the sections that everything is found. This review is really what you make of it, so go ahead. I use the chapters feature to split it up accordingly, so I recommend writing everything down, working on it, doing the quick solutions to check your work, and anything that you missed, take a look at the explanation. Best of luck. Problem number 1. Problems 2 and 3 over derivative rules. Problem number 4. Problem number 5, dealing with the relationship between position, velocity, and acceleration. This right here is showing you the best way to deal with the X and Y axes on Desmos. If you click this, it will allow you to say what you want your X axis to go to and from, same with your Y axis, so you can see the full function in the best way. And problem number 6 on geometric rates of change. In number 1, we're looking at the relationship between a function's graph and the derivative. So relationship between f and f prime. We only want to look between 0 and 2 pi on here. And we can see that the original f sine of theta increases, decreases, and then increases again. Remember, when f is increasing, that means its derivative is positive. If we were to draw tangent lines here, between when x is 0, or theta rather, when theta is 0 to pi over 2, the tangent line would have a positive slope. Therefore, the derivative is positive there. It's greater than 0. Then again, beginning at 3 pi over 2 up until 2 pi, again, that's where we're cutting off here, that is also where the original graph is increasing. Therefore, the derivative is positive there. So our derivative is positive when our original graph is increasing. And that is on the interval from 0 to pi over 2, which you can write that with parentheses around it as well. And also on the interval, and I'll write this one the other way. You can write it like this, 3 pi over 2 to 2 pi. So you can write those intervals in either way. Then when our function is decreasing, that means the derivative is negative. So our function is decreasing in between pi over 2 and 3 pi over 2. Our function decreases there. It goes down from left to right. Therefore, the derivative is negative there. So the derivative is negative in between pi over 2 and 3 pi over 2. And our derivative equals 0 when we have a horizontal tangent, because the derivative is the slope of the tangent line. And that is when our function is neither increasing nor decreasing. We can see here if we drew the tangent line, the derivative is 0 there because the slope of a horizontal line is 0. Therefore, f prime equals 0 at exactly when theta equals pi over 2 and 3 pi over 2. And in this case, those happen to be local max and min values. In problem number 2, we want to find each derivative. And I'm going to just rewrite part A down here at the bottom. I'm going to rewrite 6 over x cubed as 6x to the negative third. So it looks like a power. Then this term looks like a power already, and then this is 5x to the 1/2 because a square root is a 1/2 power. That allows us to find the derivative much simpler using the power rule for each term. Our first term, we'll bring the negative 3 out front and multiply it by the 6, and then subtract 1 in our exponent. For the second term, we'll do the same thing, bring that 2 out front and multiply it by the minus 11, and then subtract 1 in our exponent. And then the same thing for our final term, bring the 1/2 out front, multiply it by the 5, and subtract 1. Now, depending on if this is a multiple choice question, which it most likely will be, the answers will be written properly, meaning they'll have positive exponents only, and therefore we can write this first term as negative 18 over x to the 4th. This is just minus 22x, and x to the negative 1/2 means the square root of x, but it's in the denominator since the 1/2 is negative. And so that is how this would likely be written in proper notation for part A. For part B, we can use the product rule, or we can use algebra first by multiplying everything out and then using the power rule again. It's up to you. I'm going to use the product rule so we can get practice with it. So actually, instead of writing y equals, I'm just going to write the u and the v, and then we can use our product rule. So u equals 8x squared plus 1, and v equals negative 2x minus 3x cubed. Then u prime, taking the derivative of u, is 16x using the power rule, and v prime using the power rule is negative 2 minus 9x squared. The product rule tells us that if we're multiplying two things together and we want to take its derivative, it's u times v prime plus v times u prime. So writing this all out, we will have u times v prime, which is 8x squared plus 1, times v prime, negative 2 minus 9x squared, plus vu prime. V is negative 2x minus 3x cubed, and u prime is 16x. Then when we multiply this all out, so this is dy dx since we found the derivative. When we multiply this all out, we'll have negative 16x squared minus 72x to the 4th. Then distributing the 1, we'll have minus 2 minus 9x squared. Then we will distribute the 16x through. You can put those arrows either way. So we'll have minus 32x squared minus 48x to the 4th. Then we want to combine some like terms. So it'll give us negative 120 x to the 4th. Then we have a lot of x squareds. That'll give us minus 57x squared, and then a minus 2. Now, if you ended up doing this the other way, you should still get the same final answer for part B. For part C, you can either use the quotient rule or you can simplify. I'm actually going to show you how you can just simplify this, although using the quotient rule is possible too. T of c, and then we can write this as c cubed over c to the 5th, minus 4c to the 8th over c to the 5th, since they have that common denominator of c to the 5th. Then canceling, our first term ends up becoming 1 over c squared, and our second term ends up becoming minus 4c to the 3rd when our exponents cancel through subtraction. And then you can end up rewriting the first term as c to the negative 2nd, and the second term can just stay as that. So that's t of c. Then when we find t prime to find the derivative, we're taking the derivative of this right here using the power rule twice. So we'll bring the negative 2 out front and subtract 1 in our exponent, bring the 3 out front and multiply by the 4 and then subtract 1. Writing with positive exponents will be negative 2 over c cubed and then minus 12c squared. Now, what if you decided to use the quotient rule? So what if you decided to use the quotient rule here? The quotient rule is low d high minus high d low all over low squared. So t of c, I'll just rewrite it, is c cubed minus 4c to the 8th all over c to the 5th. So the derivative is low times the derivative of the high. The derivative of the numerator is 3c squared minus 32c to the 7th, running out of room. Low d high minus high d low. And d low is 5c to the 4th all over low squared, which is c to the 5th, squared, which is c to the 10th. Then when we keep going to simplify this, this part is just all algebra, and we'll distribute the c to the 5th, so we'll have 3c to the 7th minus 32c to the 12th. And then I'm going to still have this subtracted, and then we're going to do this multiplication in here. So be careful about your order of operations. We're going to multiply first here. So we'll have 5c to the 7th, and then we'll have minus 20c to the 12th. Then when we distribute that minus sign through, what that'll end up looking like is we'll have a minus 5c to the 7th and then a plus 20c to the 12th. So I just distributed the minus sign through, and when I did that, got rid of those parentheses there. Okay, this is all over again c to the 10th. Then I'm going to combine some like terms. It looks like we'll have a negative 12c to the 12th, and we'll have a minus 2c to the 7th, and then that's all over c to the 10th, which we can write as two separate fractions if you want to simplify it more easily. And our first term, c to the 12th over c to the 10th, would be c squared, so negative 12c squared, then minus 2 over c cubed. So either way we get the same thing. The terms are just written in a different order. It doesn't matter. So we have our derivative either way. I think that the quotient rule is much more difficult in that sense, but just making sure that in case you do need to use the quotient rule that you know how. In problem number 3, we want to find g double prime, and so that just means we're going to find two derivatives, the derivative of the derivative. So I'm actually going to rewrite g of x and not do any calculus just yet. I'm going to rewrite g of x so we can use the power rule more easily. It's 3x to the negative 1 minus 5x plus 2. Then I'm going to find the first derivative, g prime, using the power rule. That's negative 3x to the negative 2. The derivative of minus 5x is minus 5, and the derivative of plus 2 is 0, so that goes away. Then we need to find the derivative of that, which is the second derivative, g double prime, using again the power rule, multiplying, and then going one less, and the derivative of minus 5 is 0, so that goes away. Writing this with positive exponents gives us 6 over x cubed as our second derivative. In number 4, in order to find horizontal tangents, we need to figure out when does the derivative equal 0, because that is when we would have a horizontal tangent line, meaning its slope would be 0. So the first thing we need to do is find f prime, and we can do that using the power rule here. So we'll bring the 4 out to the front. 4 times 3/4 is 3. And then subtract 1 in the exponent. Do the same thing for the next term. 2 times 15/2 is 15, so minus 15x to the first. And the derivative of 7/4, which is a constant, is just 0. The next thing that we need to do is set this derivative equal to 0, because that'll give us when our tangent line is horizontal. When is the derivative 0? Now, when we have something that looks like this, our first instinct is to factor. That's the first thing we should do when we have something set to 0. And so we can factor out the greatest common factor of 3x. We will be left with x squared minus 5. We cannot further factor that quadratic binomial because it's not a difference of squares. So what we're going to do instead is use the zero product property and set each one of our factors equal to 0. So we'll have 3x equals 0, and we'll have x squared minus 5 equals 0. Dividing both sides by 3, x equals 0 is one solution. Adding 5 to both sides, and then taking the square root. And of course, since we're taking the square root of both sides, we do have to put a plus or minus in front when we are solving an equation and taking the square root of both sides. That is just saying that x could have either been plus or minus the square root of 5. So the horizontal tangents occur at x equals negative root 5, 0, and positive root 5. I'm just writing them in order from least to greatest. For number 5, our space shuttle problem, I put the graph in Desmos and it is ridiculous looking because it's so narrow. What I want to do is basically not have so much space to the left and to the right on our x-axis, and the way that we can do that is by hitting this like wrench button up top here. I don't know my tools very well, so I think that's a wrench button. On the x-axis, I don't want to go too far in the negative direction, so I'm just going to go maybe like -50. And then our greatest x, it looks like it's not too much past 100. I'll just do 150. And then my y-axis is fine the way it is. So that looks so much better. I can just more easily see it. I didn't even need all the way to 150. I didn't realize how far it went. I couldn't see, but really, you can kind of just mess with that so your graph isn't so awkward looking. It's a little easier to look at now. All right, so we can see that this is the height of the space shuttle over time. And it looks like our space shuttle's height increases and then decreases, meaning it comes back to the ground, like, 58 seconds or so. We are asked to figure out when is the velocity positive. Now this is the position function here, the height function. So since this is the position function, its derivative is going to be velocity. And the relationship between a function and its derivative is that if its original function is increasing, that means its derivative is positive. Therefore, when our position function is increasing, the velocity is positive. So our velocity is positive when this position function or height function is increasing. And in order to see what that coordinate point is up there, we can just click on it. And it looks like our velocity is positive from the start, from 0 until 28.125 seconds. So for part B, our velocity is positive from time 0 to time 28.125, and our velocity is negative when our function begins to decrease, which is from that time 28.125 until we hit the ground, which we will see is down here at 56.25 seconds. In order to find the velocity function, what we need to do is take the derivative of the position function. So the derivative of our height or position function is the velocity function. And that is going to be 45 using the power rule, and then using the power rule again is 1.6 t. So that's our velocity function. And then we want to find the acceleration function, which is the derivative of velocity. So acceleration is the derivative of velocity, and the derivative of our velocity function above, right here, this derivative of a constant 45 is 0. The derivative of minus 1.6 t is just minus 1.6. Our last problem here is about geometric rates of change, and we're talking about a rectangle that has a height that is 3 times its base length b. So the first thing I'm going to do is just draw a picture of this rectangle, and its height needs to be 3 times the base length b. So I'm going to call the base length b, and I'm going to call the height 3b, since I don't want to introduce a new variable. I only want these 2 variables, and it's 3 times b. So that's not too bad. Then we need to find the instantaneous rate of change of the area with respect to b. Before we can find the instantaneous rate of change of the area, we need to just find the area. So the area of a rectangle is base times height, which in this case is b times 3b. So it's b times 3b. So area is 3b squared of this particular rectangle here. Now, in order to find the instantaneous rate of change of A with respect to B, I'm going to find the derivative of this right here. So it's the derivative of the area A with respect to our variable B, dA dB, To find the derivative of a equals 3b squared, I just use the power rule. B is our variable. And I bring the 2 out front and multiply it by the 3, and b is now to the first power. So that is our rate of change, dA dB. For part B, we need to find dA dB when b equals 4, meaning I'm going to plug 4 in for b, and it's going to be 24. I'm going to put units on this. The units for this are the units of our area, which is just units squared. I didn't say what the particular unit is. Units squared per unit. I didn't say centimeter or inches or anything like that. And so we can also say that this is units squared or squared units per unit, since it's area changing with respect to base length. Here are a quick run through of the solutions. Pause whenever you need to. Problem 1. Note that you can write these intervals looking like this or looking like this. Either way is fine. Problem 2. And 3. Problem number 4. Problem 5. And number 6. Happy studying and good luck.